Hello, welcome to session 2. And from here, we're going to pick from where Mrs. Woody has left. Woody was looking at current in both series and parallel. I will pick at current and at voltage in both parallel and also series as well. So, voltage in series arrangement, we can now this diagram that will help us learn more about it. We have a lamp or a bulb. Across this of the voltmeters, there's a switch at this particular point. Another lamp, and again another voltmeters here. Then a source of power, that is the cells are here. Now, this voltage, we can label them maybe this one as V1, V2, and V3. So of course, when this switch is closed, the current flow and this voltmeters will indicate some readings. So we will be having a reading in voltmeter 1, voltmeter 2, and voltmeter 3. So in series arrangement, we will find that the supply voltage is around these two cells, which you can call it V4. If you are using the normal drive, which is 1.5 volt each, then if there are two, we expect to see a reading here of 3 volts. This is the supply voltage. But when this switch is closed, we will be having a reading at 1, reading at 2, and a reading at 3. So in this arrangement, reading in V1 plus reading in V2 plus reading in V3 will be the same as the supply voltage, same as the reading in V4. So maybe if we know the 3, if you know the 2, we can get the third one. So just add and then it will be equal to this. So reading here plus reading here plus reading here will always be the same as the total supply voltage. That should mean if the reading are different, the reading may be different depending on the strength or the resistance of these lamps, of these bulbs. Now, we can now say, therefore, in conclusion, that when a component are connected in series, then the sum of voltage across each component is the same as the total supply voltage. So, across each component, the same as the supply voltage, which is 3 volts for that particular point. Now, let us move at voltage in parallel. Voltage in parallel arrangement. Parallel arrangement, they are placed positive, positive, negative, negative. The best diagram, you can use this one here. You can call this is V1. We call this one is V2, and then V3 will be down here. Then the supplying voltage we have down here. And the switch. Now, so it is voltage across each lamp, voltmeter 1, voltmeter 2, voltmeter 3, and then the supplying voltage is here, it's voltmeter 4. So if we are using the two cells, which is 1.5 voltage each, then we expect to see the reading of 3 volts at this particular point across this one. But a different reading on each V1, V2, and V3. So when this switch is closed, we'll realize that the reading, close the switch, you'll realize that the reading in V1 equals to reading in V2, equals to reading in V3, equals to reading in V4. So in parallel arrangement, we'll have the same reading. So we'll see 3V here, 3V here, 3V here, 3V here. So we have the same or common reading across each component in parallel arrangement. And therefore, we can now conclude, and then we say that when the components are connected in parallel, the same voltage drop is noted across each component. So the same V, the same V, the same V, the same V. However, in series, it was the sum of this V1, V2, V3 was the same as the supplying voltage. So there's that difference in series and in parallel. That is not the difference in that particular point. Now, having known how we can measure and record the voltmeter reading and the ammeter reading in both series and the parallel, we can now move to the next subtopic, which is known as the Ohm's law. Ohm's law. This Ohms is a German physicist who studied the relationship between voltage and current flowing across a conductor. When you have your circuit with the voltmeter, ammeter connected, then when the switch is closed, there will be reading which is flowing through. So the way current flows and the way voltage flows, there is a relationship between those two, which was discovered and studied by this German physicist which is called George Ohms. So in verifying this law, we may require some of the following as our apparatus. We may require dry cells as the source of power. We may require ammeter. We may require voltmeter. We require connecting wires. We will also require variable resistor. In our case, we can use either potentiometer or a rheostat. Then we also require a nichrome wire. Nichrome wire or resistance wire. So these things, when we have our diagram, this time we can have a simple circuit to help us study this. Our simple circuit It's just this one here. Then in series connection, positive, negative. Then we have our ammeter. Voltmeters is across the resistance. What is the resistance of the nickel wire? Then connecting wire. Which potentiometer or specifically rheostat is this one here, is the variable resistor. Nichrome wire we placed here, and then the switch is here. Now, this variable resistor, when we adjust it either clockwise or anti-clockwise, will vary the current and the voltage. So any adjustment made on the variable resistor will have a specific value on both ammeter and voltmeter. Now, so when you have a table, for example, you can have a small table whereby we'll have the ammeter reading for current and voltmeter reading for voltage. So any slight adjustment on the variable resistor, they'll be a reading in both voltmeter and ammeter. Maybe to say current may be 0.1, voltmeter maybe 0.4, for example. Then if you adjust again, maybe in an increasing way, maybe loud, maybe 0.2, maybe 0.5. Again, if you adjust 0.3, maybe 0.6, as we move on up, and then we get a desired value, or we get a value which can help us plot a graph. Now, in this particular point, we realize that when we adjust, when we increase or we adjust the variable resistor, we notice an increase value in current and an increase value in voltage. So this thing can be done, and then we get as many values as possible, and then we complete the table. Then from there, we can now have our graph so that we see how these things are related. We can decide to plot a graph of voltage against current. A graph of voltage against current. So this graph, we draw it and we label the axis, so it is voltage. We write voltage. This voltage is in volts, the unit, and current. Unit of current is ampere. Abbreviation I, and then unit ampere. So the way these values are moving, it means that when one increases, another one also increases. So increase, another one also results in increase in the other one. So this graph will be straight through the origin. So graph will still through the origin. A graph of voltage and current will straight through the origin. Now this tells us that wherever there is an increase in current, there's also a corresponding increase in voltage. So from here we can now make our conclusion on what this Ohm's law is all about. And then we say, now we can now give our comment, and then we say that increase in current result to an increase in voltage. So in this law, you can now state that the Ohm's law say that Ohm's law the current through a conductor is directly proportional to potential difference across its terminal, provided that temperature and other physical factors are kept constant. The physical factors are kept constant. That current flowing through a conductor is directly proportional to the potential difference. The potential difference here is the voltage. So current flowing through a conductor is directly proportional to potential difference across the terminal, provided that the temperature and other physical factors are kept constant. So these are the conditions. Now, this law here, the way we state it, we can also express it mathematically. We can also express it mathematically. So we can say mathematical expression of Ohm's law. So voltage flowing is proportional to the current. Now, whenever we remove this constant of proportionality, we'll put an equal sign and we'll introduce a constant. We call it R, Ri. So this constant here, we call it resistance. So we say V equal to IR in that order, whereby I is current, V is voltage, and R is resistance. We will know what resistance is later on. Now we can say where V is voltage, I current, and R resistance. So this is how we also express Ohm's law. But remember, we are saying that temperature and other physical factors must be kept constant. What is these other physical factors? Other physical factors maybe, suppose we are doing this experiment, we are having this thing called connecting wires. Now, connecting wires, if I do this experiment, you must ensure that you use the same wire throughout, the wire of the same size. It means it may be cross-section area of the wire, or those wires which you are using for that particular experiment, you must maintain their length throughout the experiment. So also length of the wire. So those two are the physical factors which must be kept constant. It means for a given practical, for a given experiment, you need to maintain the length and also maintain the thickness or the cross-section area of the wire used in that experiment. Those are the other two other physical factors which we can say are also affecting or may affect the Ohm's law. Now there is this thing which we call resistance. This resistance is resistance is the opposition offered to the flow of current. The opposition offered to the flow of current. So as current flows in the circuit, it sometimes faces some opposition, whereby when it faces that opposition, the value may either reduce. So instead of a higher current flowing, then a small current may be flowing. So this resistance or this opposition offered to the flow of current is what we call resistance. This resistance, the unit, or rather the SI unit, is ohms. Written or abbreviation that. So when we play with that formula, with this formula, whereby V equal to IR, we can get each and every quantity. I will be V over R. R will be V over I. So in this particular point, unit is volts. This particular point, unit is ampere. This particular point, unit is ohms. So we can get every quantity using this formula above. Now, this resistance ohms, which is in ohms, we can also get it through calculation given values of current and voltage, or we can also calculate it from the experiment of Ohm's law using the graph which we have. Assume that our graph from Ohm's law was, which was V against I, was straight line. So if whenever we want to get the resistance in this particular experiment, then what we do, we simply get the slope. You simply get the slope of this graph. So slope will be changed here, changing V over change in current. So we're getting current from this point. There's a value here from this point to this point. That will be change in current. Then change in voltage will be from this point apart from this upper point, will give us change in voltage. So slope, which is now the same as the resistance, will be change in V over change in I. And we therefore give the unit as ohms. So that is how we can also express, or we can also find the resistance from a graph. In some cases, learners, you can be given maybe a graph, maybe a values of voltage and current, and then you are asked to plot a graph of voltage against current, of which you will be plotting, and then you come up with a straight line. Then from there you will be also asked to find the slope. Find the slope, maybe 2 marks for example, and then next you will be told to state the quantity represented by the slope. So we are saying here, but in this particular point, slope represent the resistance. So we will say slope represent resistance of the wire used. So this is what we write at that particular point. Again, in some cases, apart from plotting a graph of voltage against resistance or voltage against current, you can also plot a graph of current against voltage. All the way to still be straight line through the origin. But now, when we are now asked to find the slope, we'll just get it the normal way. But if we are asked to find the resistance, so in this particular graph, in a graph of I versus or against V, our resistance will now be 1 over slope, or the inverse of the slope. So you don't forget. We'll get the slope, and then we get its inverse. So it will be the inverse of the slope. So we should not forget. Come on, voltage against current, slope straight away gives us current, give us resistance. Come on, the graph of I against V, slope will give us the inverse of the resistance. Now, as we do this experiment of Ohm's law, I said that we were using our apparatus were as follows. Our apparatus were dry cells. Another one were connecting wires. We also having a switch. Both ammeter and voltmeter you are using. We are also having variable resistor, which will either be potentiometer or a rheostat. Then you are having a nichrome wire. Maintaining all these apparatus except the last one. This last one can be changed. You can change it instead of using this nichrome wire. You can even decide whether it's nichrome wire, you replace it with maybe a touch bulb, or you put maybe a diode, or you put maybe an electrolyte. So we can always be changing this, and whenever we change this, we will be getting a different graph. There are some graphs which if you carry it out using this experiment, then in some cases the graph may fail the straight line to the origin. But it will now be a curve. It can be a curve or it can be straight line, depending on what we use instead of nichrome wire. Now this brings me to what is called harmonic and non-harmonic conductor. Harmonic and non-harmonic conductors. Now, harmonic conductors these are conductors which obeys Ohm's law. These are conductors which obeys Ohm's law. It means if you use them in experiment in place of nichrome wire, then the graph will be straight line to the origin. That is harmonic conductor. The graph it across straight line. While for the other case, these harmonic conductors, we can have example of harmonic conductors are harmonic conductors example we have like the nichrome wire. So e.g. nichrome wire. Now for non-harmonic conductor, we say these are conductors which do not obey Ohm's law. They do not obey Ohm's law. If you use them, the graph won't be straight line through the origin. The graph will not be straight line through the origin. So if you use non-harmonic conductor, your graph of V against I can be of this nature. It can be like this, this way. So this is different material. It can be that way. So it won't be straight line in the origin. So example of this non-harmonic conductor, we have what? Thermistor Eg. So in this particular point, we have Eg, thermistor, torch bulbs. We have semiconductor diode, diodes, and etc. So using these conductors in place of nichrome wire, then our graph cannot be straight line. Lazima itakuwa this of that particular shape. That is what we expect in that particular point. So we are saying that harmonic conductor obeys Ohm's law. Itakuwa straight line to the origin. Non-harmonic conductor do not obey Ohm's law, and therefore the graph is somehow a curve. Now next we will move to electrical resistance. Electrical resistance as I told you before, that this is the opposition offered to the flow of current. Opposition offered to the flow of current. Now, sometimes when current tries to flow, it may tend to face some opposition, and therefore its movement may be impeded and it may not move or it may not flow as required. It always occurs when a charge flowing through a conductor has its movement impeded. When a charge flowing through a conductor has its movement restricted or its movement impeded. And this one can be caused by collisions, maybe between the atoms of the material and electrons. Remember, if you have a conductor, if this is a conductor, metallic conductor, for example, this conductor has got atoms. It has got atoms in it. Now, these atoms may vibrate when the temperature of this metal increases. When the temperature is raised, then these atoms may vibrate. As this atom vibrates and move across, then when current was also flowing, then atoms also vibrates. Then these atoms may cause collisions between the atoms and this current and these electrons, and therefore will have what is called electrical resistance. Their movement will now be slowed. If you were to move very fast, they will be moving slowly because their movement has been restricted or has been reduced by the collisions between the atoms of those particular metal. Now, these collisions may again lead to loss of their momentum as they move, and we may end up failing to get the correct or the desired current. Now, for us to know the resistance of a particular material, then we may require an instrument. We may use an instrument called ohmmeter. This ohmmeter will measure the resistance. So we can know the one which is having higher resistance and low resistance. Now, there are factors which may affect this electrical resistance. One of the factors affecting electrical resistance one factor is temperature. Temperature, this is how temperature may affect resistance. When you connect the apparatus, when apparatuses are connected, and as current flow, during this experiment, when we have our cells, we have our ammeter, we have our variable resistor, Then we have got nichrome wire. Our switch is here. Then we have got the voltage across this resistance wire. Now, when this switch is closed, current flow. And as current flow, the system or the circuit become warm. It gains some heat and the circuit becomes warm. If you come and touch this battery, then there will be some feeling warm. So that rise in temperature tells us that these conductors are now becomes, or their temperatures will raise slightly. When temperature is raised, then the atoms of these metals, of these conductors, will start vibrating. When atoms vibrate, then there will be collision between the atoms and electrons as the electrons are moving. And that collision interferes with the movement and therefore enhance resistance. So we can say that this happens when the atoms of a conductor, atoms of a metallic conductor gains heat and starts vibrating, leading to collision with electrons, collisions of electrons. This causes resistance. So as temperature is high, vibrations will be high, and then collision will also be high, and resistance will be enhanced. And therefore, for us to control this during this experiment, we should be opening the switch and closing at regular time, not closing it throughout. If you close it throughout, then the heat will build up and resistance will be higher. So it should always be controlled by closing and opening it at some given time, and therefore we reduce that heat which is building up and causing resistance of the conductor. Now, number two is length. Number two is length of the conductor. Length, this is one factor, length of the conductor. Conductor here are the connecting wires. These connecting wires, how should we control them so that we minimize resistance? So we find that the length of the conductor is directly proportional to resistance. This means the longer the length, the higher the resistance. So if you use a longer connecting wires, then you are at the risk of causing more resistance, and you will again realize or notice a very slight or a very small current flowing. So the longer the length, the higher the resistance, and vice versa. Let me write here. The longer the length, the higher the resistance. of a metallic conductor. And vice versa. And vice versa. It means that now the opposite is that the shorter the length, the lower the resistance of a metallic conductor. Number three, the third factor is what we call cross-section area. Cross-sectional area of the conductor. Conductor in this case refers to the connecting wires. These are the conductor. Now, through experiment, we realize that cross-section area of a metallic conductor is inversely proportional to resistance. This means the thicker the wire, the lower the resistance. If you use a thicker wire or a wire of a bigger cross-section area, the resistance is being reduced. That is what this statement means. It is inversely proportional to resistance. So the thicker the wire, the lower the resistance. The thicker the wire, the lower the resistance. The lower the resistance. And vice versa. Now, we can combine these two statements. From factor number two, which was the length, we were saying that length was directly proportional. So length directly proportional to resistance. The length is directly proportional to resistance. So we therefore can say L equal to, we can use this constant proportionality. That constant proportionality, you can use it that it is directly proportional to that. Then, if you want to get R, this resistance, we divide both sides by. So R is L over that constant. That value we use it as a constant of proportionality. Now in our second factor here, we are saying that resistance is inversely proportional to cross-sectional area. So if you work with this, you will say R equal to a constant area. R equals to a constant, then divide by that area. Now, if you combine those two, 1 and 2, so that we form 1, we will therefore say combine 1 and 2. If you combine 1 and 2, we will therefore say that resistance is resistance is directly proportional to length and inversely proportional to area. And to remove the constantity, then we say R equal to a constant L over A. So this constant, of which if we are looking for it, this constant will be, it will have been, it was multiplied, it would have been AR over L. So this constant here is called resistivity. Resistivity. So resistivity is given by area, cross-section area, resistance divided by length. Now, this thing here, we can tend to get maybe you know its unit. This unit of area is in square meter. Then this unit of resistance is ohms. This unit of length is meters. So if we divide this, then we'll end up with this resistivity, the unit of resistivity to be ohm meter. So we can say the SI unit of resistivity is ohm meter, written as ohm meter. Now when you calculate these values, you should ensure that all of them are in their SI unit. Sometimes the area may be in square millimeters or square centimeters, length may be in millimeters or centimeters. Then you have to convert them to their respective SI units so that we'll be able to find them or we'll be able to get what is required. Now, in summary, as we conclude, we have looked at Ohm's law, of which we have stated as current flowing through a conductor is directly proportional to potential difference across the terminal, provided that the temperature and other physical factors are kept constant. And the physical factors are kept constant. Those physical factors will be similarly length of the conductor and again cross-sectional area of that conductor. So those factors must be kept constant. Again, we have said that in this experiment of Ohm's law, if we plot a graph of current against voltage, voltage against current, and this is a straight line to the origin, of which the slope will give us the resistance. Slope will give us R because we'll be changing V over changing R, over changing I. Unit of resistance is ohm. If we interchange the axis, we have, instead of having V against I, we have I against V. Then R, resistance, will be 1 over the inverse of the slope, or will be the same as the inverse of the slope, or 1 over slope. That will be the resistance. Then we also came to ohmic and non-ohmic conductors, where we said that ohmic conductors obey Ohm's law. And if you use them in your experiment or in your practical, then you expect a straight line graph which passed through the origin. Non-ohmic conductors do not obey Ohm's law. If you use them in your experiment, the graph is going to be a curve. So those non-ohmic conductors, they are like thermistor, diode, torch bulb, etc. Those ones, if you use them in your experiment, then your graph will be a curve because they don't obey Ohm's law. Then we also came to factors affecting resistance, nominally conductor. These factors, we said there are three. One, temperature. Temperature affects resistance, as in when temperature builds up, atoms get excited and then they start moving. As they move, they create collisions with electrons, and then therefore they cause what they enhance resistance. Two is length. We said the longer the length, the higher the resistance, and vice versa. Cross-sectional area, we said the thicker the wire, the lower the resistance. If a wire is thick, the resistance is low, so it is inversely proportional. Then if you combine those two, we come here. So this constant quantity here is called resistivity. So resistivity is given by cross-sectional area times resistance divided by length, of which if you try to look at its unit, the SI unit now becomes ohm meter, written as ohm meter. That is now the SI unit of resistance. Allow me to stop there, and I thank you for participating. We'll have another class next week. Timetable, I think, is out. We encourage you that if you have a question, you post in the comment and you post with your name and your stream. So your name and your stream, then you ask that question. We may react, we may answer it even later in the next lesson if we meet there, if time doesn't allow us to answer it now. Again, we will give you assignment in your various walls and you'll be able to do and maybe go through it when we meet. Otherwise, thank you and have a nice lunch. Hey.